recall that one of the benefits of being a SaaS business is that you get continual visibility into user behavior, because users are continually interacting with your central servers in order to use your products, so you can just log what they do. In this section, we're going to look at how SaaS companies can record and make sense of huge quantities of interaction data. Now, the field of turning user interaction data into actionable insights that can inform product roadmaps and product development is called behavioural analytics. And we're going to look at how behavioural analytics systems are architected, and then show how they can be made more powerful by augmenting them with what are called experiment frameworks to test hypotheses about user behaviour scientifically and understand cause and effect. So at a high level, here is what a simple behavioural analytics framework looks like. A unique ID is associated with each user. Where this ID comes from is dependent on the system, but in the case of a website, for example, it might be a cookie that contains a random unique identifier that is set by the website the first time a user accesses it. From that point on, each action that a user performs is logged. So each log line typically records the who, what, when of an event. For example, a log line may encode that a user with ID U clicked button B at time T. Now, the SaaS service itself contains code that writes a log line on each user event. And it typically writes this log line just by calling a simple logging API on web services called analytics collectors. And these analytics collectors are very simple services that just ensure that the log line is written to an OLAP, online analytics processing. That is, you probably remember that from the database course, an OLAP database that stores a big long time series of all events logged across all users. So then data pipelines would then typically process these raw logs, maybe real time or maybe batch, in order to transform and enrich them. For example, a client IP address may be transformed into an approximate geographic location with the latitude and longitude of the approximate location written back to the log line as an additional data point, and the IP address deleted. Then the time series of enriched log lines are then used as the data source for business reports, automatically generated business reports on the one hand, and to support ad hoc queries that analysts and product managers might run in order to answer specific business questions. So what can we learn from the types of user events in the OLAP database? What sort of reports might we want to run, or queries might we want to run against this time series? Well, one very common business report is just to generate the number of users that access the site. Typically, all of these metrics would be generated, say, daily, and then graphs used to sort of see what the trends are on these metrics. So in order to count users and not just the number of events, this involves computing the set of user IDs, so the deduplicated user IDs that access the site in some time period, and then computing the cardinality of that set. So DAU stands for daily active users. So this would be the cardinality of the set of unique users who accessed the site in the last 24 hours. And MAU stands for monthly active unique users. This would be the number of unique user IDs that was seen over a trailing 30-day period. Typically, people use trailing 30 days rather than actually in a given month, because that gets around the inconvenience that our months are variable lengths, and therefore so counting by month actually induces variability that you really don't want. So typically, monthly active users would be the number of user IDs seen in a trailing 30-day window. Now, engagement metrics can also be calculated. So one common engagement metric that actually isn't on this slide is just taking the ratio of DAU divided by MAU. So if this ratio is 100%, it means that your monthly users typically access your site daily, so they're very engaged. But if this ratio was lower, say about 13%, it would mean that your monthly user base is made up of people who access your product about once a week on average, so they're less engaged. An alternative way to measure user engagement is by just calculating the time spent using the service per user session. So you would just take the event log that spanned the duration of one user's session and you would just subtract the last time on the last log event from the first time where the user logged in. Now, engagement and user numbers are interesting, but they're really sort of macroeconomic indicators in the sense that they give you some high-level understanding of business and product health, but they give you little insight into what is really going on. So to gain more insights, you can start considering usage, growth, and engagement metrics for specific features. So for example, you might look at DAU to MAU ratios for a particular feature, or different per feature usage and growth metrics, such as the ones shown on this slide. So, if you're a music streaming service, maybe you look at the feature usage of people who's actually playing songs, just to make sure that people are really using your service, as opposed to just opening the app and then closing it again without really engaging. Now, another common use of analytics, to get even more granular insights, is to compare the behavior of different segments of users. So this relies on having some demographic data about your users so that you can segment them appropriately. But if you're a service where maybe users sign up and provide some personal information as part of an account creation step, then this data may be directly accessible. So now by just querying the data in the right ways, you can generate insights such as how specific segments of users interacted with given features. For example, you might be able to compare the segment of female users aged between 20 to 25, and you might say that they're X% more likely to use feature F at least once, as opposed to, say, the average user. Now, we can also explore correlations from behavioural analytics logs. For example, we might observe that the usage of one feature is correlated with the usage of another, or we might observe that the user engagement increases as the number of days since sign-up increases. However, although we can determine correlations, we cannot determine causality. For example, in the case of feature usage correlation, although the usage itself may be correlated, it might not be the usage of F2 that causes the usage of F1. It might instead be that there is some hidden variable, like the user's age, for example, that is behind the usage of both F2 and F1. So in this case, it would really be the fact, say, that a user is younger that actually causes the adoption of both F2 and F1, not the fact that the usage of F2 causes the adoption of F1. Now, not being able to determine causality is a problem, because if we implement a change to our software, and let's say our engagement or revenue numbers increase, then we really want to know whether or not the change that we made caused those increases, or whether it was just down to coincidence or down to other factors. Now, it's so important to understand causality that SaaS companies go to great lengths to solve it. And they solve the problem by determining causality by building experiment frameworks and then continually running controlled experiments. So let's look at what controlled experiments are in this context and see what they can tell us. Now, if we don't run controlled experiments, then the best you can do to try and understand the impact of a particular change is just to look at your measurements before and after you make the change, and just sort of eyeball it and see if you think whether the change made a difference or not. Now, this is clearly unscientific, but sometimes it can be just about good enough if the thing you changed made a huge difference and you can really see it. But more often than not, though, the kinds of changes that you're making on fairly mature SaaS products actually make quite small differences to your key metrics. These changes are still worth making because if you do a lot of them, they still add up to large improvements, but in and of themselves, they make differences that are small enough that you really can't tell if all you're doing is looking at before versus after differences in numbers to try and figure out whether your change actually made any differences or whether those differences were down to other factors. Such as, for example, the fact that traffic volumes and user behavior may be very different on a Saturday than they are on a Friday. So, if you compare differences before or after a change you made on a Friday, any differences you observe will probably be just down to the fact that it's a weekend and not a weekday, for example. The scientific approach here is to use a controlled experiment. So instead of taking a look before and after, instead we separate users into a control group and an experiment group. And we then release the change to the experiment group only, but we hold it back from the control group. Then an experiment would run over a period of time during which we would record the differences in the key measures between those in the experiment group and those in the control group, and we would then test for statistical significance. Now, as long as the control and experiment groups are randomly selected, the only difference between them that could be causing the observed changes in our measurements is the fact that one group has been exposed to the software product change that we made and one hasn't. Therefore, since all extraneous variables have been controlled for, i.e. averaged out across the randomly selected experiment and control groups, then the measured differences between the experiment and control groups can be causally attributed to the product change. Now, an experiment framework lets you manage all of this in the context of a SaaS product. So it deals with randomly grouping users into experiment and control groups, managing the rollout of features to experiment groups only and holding them back from control groups, measuring the difference between experiment and control groups on key metrics, and determining when statistical significance has been reached. Now, an important input into experiment frameworks is, for a given experiment, what percentage of users should be in the experiment group and what percentage should be in the control group. So this is signified as E on this slide and the next few slides. A common technique is to start with a low E and then ramp it up. And the rationale here is risk management. So similar to a rolling deploy, we want to start small and check the metrics are sort of looking okay-ish before we ramp up to 50%. And at 50%, this is where we can get to statistical significance fastest because we've got balanced experiment and control groups. And we just start small because we want to make sure that our key measures aren't looking hugely negative before we increase exposure and potentially impact the business. Now, one interesting observation here is that products or companies with larger user bases can test faster. And this is because statistical significance is achieved faster when there are more samples in the experiment. Now, the speed at which you can record experiment samples depends on the number of users you have. So therefore, the speed at which you can determine statistical significance for a given experiment is also determined by the volume of users on the product. So this is an often overlooked scale advantage that's enjoyed by larger SaaS companies. Having more users means it's faster to determine statistical significance for experiments, which allows a faster experiment throughput, and therefore in turn enables companies with larger user bases to optimize their products and business metrics more quickly than their smaller competitors. Okay, so now we've explained controlled experiments, let's have a look at a very high level at how a behavioural analytics system can be augmented with experiment capability, with the resulting combined system sometimes being referred to as an A/B testing platform. So at a very high level, here's how a simple A/B testing platform might work. So recall that we already have a persistent user ID for each user, let's call it UID, and let's also assign an ID to each active experiment, we'll call it EID. And then we'll let E be the exposure, i.e. the percentage of users as an integer between 0 and 100 who are exposed in the experiment group to experiment EID. So given this, the SaaS platform, whenever a user accesses the service, can have a decision procedure for all experiments for determining whether a given user is in the experiment or control group for that experiment. And it can then return a result which either includes the change in the right experiment groups or withholds the change from the experiments where the user is in the control group. Now, a common technique, a common decision procedure for determining whether a given user, UID, is in the control or experiment group for a given experiment EID is to take a hash of the UID concatenated with the EID, mod 100, and then just check if the resulting value is less than E or not. Now, as long as we choose a good hash function, the hash of UID concatenated with EID, mod 100, just returns a number that's uniformly distributed between 0 and 99 and is independent of the structure of UID and EID. So given then that our exposure level E is an integer between 0 and 100, we can just check if this hash mod 100 here is less than E to determine whether to assign a user to the experiment group or the control group. Now, in addition to doing a pretty good job of generating unbiased control and experiment groups with E% in the experiment group, this approach has the following benefits. Firstly, users are persistently in either a control or an experiment group for a given experiment. Because this hash is consistent for a given user, it's persistent and consistent for a given user and a given experiment ID. So users don't flap between control and experiment groups on different sessions, which would obviously ruin the test. Secondly, if a user is in an experiment group for low exposure, for low E, then they remain in the experiment group as E is increased. So if we start an experiment small and then ramp it up, then we don't cause users to go from an experiment group back into a control group ever. Once you've been in an experiment group, once you're exposed to the experiment, you remain exposed to the experiment. So again, we don't have people flapping from the experiment into a control group and back, which again would sort of ruin the test. Finally, the approach works for multiple concurrent experiments, and it assigns users to independent control and experiment groups for different experiments. Now, of course, if you choose to run concurrent experiments, which most people do because it's too restrictive just to run them sequentially, then you either need to convince yourself that the experiments are independent of each other, in that being in the experiment group of one doesn't change how you behave if you're exposed to the second experiment. Or, if you're not prepared to assume that they're independent, you just have to get into much more difficult stats. Now, typically SaaS companies do just assume independence between concurrent experiments, and they just try to avoid too many experiments going on in one part of the product at a time and have some process to avoid multiple experiments that are obviously going to conflict in terms of exposure to one impacting the results of another. And typically that's good enough to get the results that are required. So having assigned users to experiment and control groups and served experiment variants and control variants of our service, then we can now extend our behavioral analytics system to augment every event log line with the set of experiment groups that a user was part of at the time that the event being recorded occurred. For example, a log line may now record that at time t, a user u, who at the time was in experiment groups for EID1 and EID5, clicked button B. And then we do our enrichment, and then we get this big time series of events for all users, but now each event also records the experiment groups that a user was in at the time that the event was generated. And now, for each metric of interest, for each experiment, we can compute the difference in the metric's average value between experiment and control groups simply by running two queries against our OLAP database. One which selects only log lines from users in the control group and computes an average of the metric we care about, and then one which selects only log lines from users in the experiment group and again computes the average. We can then compute the difference in these averages to work out the magnitude of the change caused by the experiment, the change in measurements. And we can test for statistical significance. And once we've achieved statistical significance, then we really can determine a causal relationship between the change that we deployed to our product and the difference in our observed metric. And if we're happy with the results, we can then continue to roll out the feature to 100%. And if we're not happy with the results, then we can just ramp it back down to 0% and do something else with our development time. Now, the business benefit of using experiment frameworks to understand the impact of every software change on key metrics with scientific rigor is so great that SaaS companies literally run experiments all of the time. So in a recent letter to shareholders, for example, Netflix said that they ran hundreds of controlled experiments like this on their platform in 2019. So just be aware that every time you're accessing SaaS services like Google or Netflix, for example, then you are likely an unwitting participant in at least tens, if not hundreds, of concurrently running experiments. Okay, well that brings us to the end of this lecture on software as a service engineering. And in summary, I hope I've convinced you that putting this manage, deploy, upgrade cycle into the software company as opposed to in the customer, and managing the state and the software on behalf of all users from central servers really is a profound change that has far-reaching consequences. So just to recap, we've seen that economically the SaaS model can reduce customer TCO and that it leads to increased economic efficiencies by reducing duplication across thousands or hundreds of thousands of customers, and improving specialization in terms of the way labor is divided between software companies and customers. Operationally, we saw that SaaS leads to new software development processes such as continuous deployment and new techniques for managing quality such as rolling deploys. Now, the economics of software development and quality management change considerably with SaaS because changes can be released to all customers quickly and cheaply with minimal risk, something that is not typically true in the worlds where software is distributed as binaries. We also saw how the SaaS model supports behavioral analytics and experiment frameworks, and how these tools can create data and insights that essentially allow us to involve our users in the product development process directly. Now, I'm sure that all of you use SaaS software on a daily basis, and the trends are such that many of you will probably work in SaaS companies after you graduate. So I hope I've given you some insight into how SaaS software is developed, and that I've shown you how the product and software engineering techniques that are employed in SaaS companies have, at least in some ways, evolved into something that is quite different from those used in a world where companies ship software as binaries.